Welcome everyone to another video. Today we are proving the mean value theorem. Okay, nice. How do we go on about proving this theorem? And why did I choose this one? Well, we have the extreme value theorem and the intermediate value theorem, both of which are pretty intuitive. So I thought this one is worth a proof, and I think this is maybe the easier one to prove, which is surprising. But mostly the intuitive things in math are kind of hard to prove. Now, before proving the mean value theorem, we have to have a tool. We have to acquire a tool, and that tool is Rolle's theorem. That's not an S, an apostrophe. Damn it, I can't write anything anymore. There we go. Rolle's theorem. We have to prove Rolle's theorem. And why would we do this? Why Rolle's theorem? Well, you see, Rolle's theorem is just the mean value theorem, but with an extra condition, an extra restriction. When we have extra restrictions, it's easier to prove things. For example, if I ask you to give me a formula for all odd primes, that would be difficult. But if I ask you only for a formula for the odd numbers, which is a restriction, I don't need prime numbers anymore, well, that's easy. That's just 2n plus 1 or many other formulas. So we'll go ahead and prove Rolle's theorem and build up the mean value theorem. To prove this theorem, we have to set some conditions. What are they? Well, f, our function, has to be continuous on the closed interval a to b. This means that a and b are included, and f has to be differentiable on the open interval, meaning a and b don't have to be included. Now, for the extra condition, this is where it differs from the mean value theorem. F of a has to equal f of b. And so, with these conditions, the Rolle's theorem states that there exists a C inside the open interval such that f prime of C is equal to 0. Very nice. Now, how might this help us with the mean value theorem? If you notice, f prime of C is equal to 0, but we can replace this 0 with f of B minus f of a, because f of b and f of a are the same, so they subtract to 0 over some number, which won't matter. 0 over a number is just 0. And look at that. That looks very much like the mean value theorem, and this is how it will lead us to the mean value theorem. Here we go. So I'll put the conditions in a small box, again continuous on the closed interval, differentiable on the open one, and f of a is equal to f of b. And here I've drawn a graph that could possibly represent f of x. It doesn't have to be this way. It can be constant, as we'll see soon. And this is meant to give you some intuition behind what we're trying to do. So we'll go ahead and state that by the extreme value theorem. So if you don't remember, the extreme value theorem states that on a closed interval, like from a to b, there exists at least one maximum and one minimum. Meaning, for example, here, this could be our maximum and this could be our minimum. And so we're applying it here. So by the extreme value theorem, let's say there exists at least one absolute max and one absolute min. So by the extreme value theorem, there exists at least one absolute maximum and one absolute minimum. Now is a good point to remind ourselves where these maximums and minimums occur. We know that on a closed interval, they either occur at the endpoints or possibly where the derivative is 0, such as this one, or when the derivative is undefined. And here when we say the derivative is 0, we mean on the interior, not including the endpoints, and here as well. Because we're already checking the endpoints, we'll talk about the derivatives on the open interval. Now, we know that according to the conditions, f is differentiable on the open interval, meaning it won't be undefined, and we can cross that possibility. It's inside the open interval. Now let's check the case where f prime of x is equal to 0. And this means that at some point in the open interval, we'll find either the absolute max or the absolute min. I meant it the other way around. if the absolute max or absolute min was on the open interval at some point, then the derivative will be 0 at that point. But notice, if this is true, if the second case is what we have, then Rolle's theorem holds. It is true, because Rolle's theorem says that there is an x or a c such that the derivative is 0. And so this is a check. Now to check the case where this is not true, that means we have to check the case where there is no absolute minimum or absolute maximum in the open interval. But this is exactly the case where the endpoints are both the absolute max and the absolute min at the same time. And if it is true that the endpoints are the max and the min, that means the maximum is equal to the minimum, which is equal to f of a, which is equal to f of b. That means every number that for all x inside our interval, f of a is greater than or equal to f of x, and at the same time f of a is less than or equal to f of x, and the same goes for f of b. But you realize here that if f of x is less than or equal to f of a, but at the same time greater than or equal to f of a, then it must be equal to f of a, and effectively equal to f of b. But observe here that if f of b is equal to f of a and equal to f of x for all x on the interval, then that means the function must be constant. That is a very bad line, but you get the idea, the function is constant. But if the function is constant, then it follows that f prime of x is equal to 0 for all x on that interval, because you see here the slope is 0. But then in this case, Rolle's theorem holds again. It is true. We can say that there exists a c on the open interval such that f prime of c is equal to 0. In fact, you can pick any number on the interval, but this is what Rolle's theorem wants. It wants to show you that there exists one c, at least one c, such that this is true. Okay, ladies and gentlemen, on to the mean value theorem. Now we're going to be working on under the same conditions. I'm not going to write them down, they're going to take space. But to remind you, f is differentiable on the open interval, continuous on the closed one, and f of a is not equal to f of b in this case, because we're working with an arbitrary function f, and it could look like this. It's not necessarily this, but I'm going to call this f. Now, the first thing I'm going to do is draw a secant line. So where am I going to draw this? Well, I'm going to take the interval a to b, under which the conditions are true, and I'm going to draw my secant line. That is a very thick line for some reason. And what I want to get now is the equation for this line. And let's just call it g. And so to construct an equation for a line, we need 2 points. And we have precisely that. We have a, f of a, and b, f of b. Very good. And so let's use the slope point form of the linear equation, g, our function. Let's say it's a function of x minus y naught, let's say, equal to m, the slope, times x minus x naught. Not point. How do we get y naught, x naught, and our slope m? Well, x naught, y naught are just arbitrary points that we pick, arbitrary points on the line. So I'm going to go ahead and say that y naught is f of a, and that the corresponding x naught will be a. Now, what about the slope? For the slope, we can use the points. So m is equal to, let's say, f of b minus f of a. That's the y1 minus y2, over b minus a. And so I'll replace the m and solve for g. We'll have g of x is equal to f of b minus f of a over b minus a times x minus a. And here we'll have plus f of a. I'm just gonna fit it in here. Very nice. So I've cleaned up and rewritten the equation for our line. Let's notice here an important property, that g of x is continuous and differentiable on all real numbers. Now, we don't need continuity and differentiability on all real numbers, just our interval, but we have it, so there it is. Now we're going to create a very special equation or function. We'll call it h of x. And h of x will represent the height between the two functions, well, the function and the line. And so h of x will be f of x minus g of x. And notice here that h of x is a difference of two functions that are continuous on the closed interval, differentiable on the open one, and so it itself has these properties. So let's write h of x in terms of x and other constants over here. So we'll replace g of x. So h of x is just f of x minus this over here. And so we'll have f of x minus the slope times x minus a minus f of a. And here we notice another very important property, and that is h of a is equal to, well, f of a minus this slope, I'm just going to write m, times a minus a, replacing the x, minus f of a. You see here, a minus a is 0 times the slope, all 0. F of a minus f of a is 0, so that'll be just a 0. And let's do h of b. H of b is f of b minus our slope times b minus a minus f of a. Here the denominators cancel. We'll have f of b minus f of b, and we'll have minus minus f of a minus f of a. That'll be a 0. And there it is. We have h of a and h of b, the endpoints, are equal to 0, meaning we could use our very special Rolle's theorem. We have the conditions under which Rolle's theorem works, and that guarantees us there exists a c on the open interval such that h prime of c, because h is the function under which the conditions are true. So now we can differentiate this whole thing and plug in c. So we'll have h prime of x is equal to f prime of x, and here we'll have a constant times a variable times a constant. That means the slope times a will just be 0 after differentiation, and the slope times x will be just the slope, because m times x differentiated will be m. So that'll give us a minus f of b minus f of a over b minus a. And f of a is just a constant. And now we have the c guaranteed, and we can plug that in. So h prime of c is equal to f prime of c minus f of b minus f of a over b minus a. And now we know that h prime of c is equal to 0, and so we can set this equal to 0. And I'll rearrange by moving this object to the left, but I'll write f prime of c on the left. So f of b minus f of a over b minus a. And look at that. We have just guaranteed a c such that f prime of c is equal to the slope of the secant line, and that will be the mean value theorem. Thank you so much for watching. I hope you enjoyed this. This is a very nice proof, especially when you think of it graphically. And that is not quite true. The height between the functions is vertical. But that's fine. I hope I haven't miscalculated anything, but tell me in the comments. I'll see you next time.